Okay, I'm going to look at a few problems. So these are from Ross chapter 10 at the end. The numbers may differ across editions, but you'll match them to the wording. So Ross there suggests kind of like ignore the conditions for optional stopping and just kind of apply it, see what you get, and if it makes sense. And I'll follow this advice, but I'll comment on the justification for applying the the optional stopping theorem at the end. So the first problem is problem 20. You can see the definition for the hitting time is a bit more complicated than in the previous example. We again have a Brownian motion, but now we're looking for the very first time that it hits the curve 2 minus 4t. So that curve is illustrated right below me. So at time 0, 2 minus 4t is 2. And then there is a slope of -4, in which case it's just a line. And we're looking for the first crossing time, with the first hitting time of of that line, or crossing time of that line. Here is a little bit of code that shows how you can simulate this, which is how the picture was made. And here are a few examples. So top left, the hitting time of the curve 2 minus 4t is roughly 0.4, it looks like. And then in the top right, it then increases all the way to something like 0.8. And then similar for the bottom two pictures. The last picture, the one on the bottom right, it almost takes until time 1 to cross the curve. So the question, as usual, is what's the expected value at which we cross it? And the solution is exactly kind of the same methodology that we had in the previous example. So we need to pick a martingale. We want that martingale to somehow involve the actual stopping time so that we can extract the expectation of tau. So we're looking for this term, and usually it's kind of similar martingales are used in all of these problems. And we'll see that we use the same one as in the previous to get an answer for this problem. So we're going to try the Brownian motion first, and let's see what happens. As before, the next step is to see, well, what is that martingale equal to at the hitting time? So we're going to evaluate the Brownian motion at time tau, and by definition there's only one possibility. If the first time at which we touch or cross or hit the curve 2 minus 4t, if that's the first time, that's going to be the value. So w at time tau is going to be 2 minus 4 tau. That's the only possibility. So it's a little bit different than the escape problem, where we had two possible choices: either hit the bottom boundary -1 or the top boundary +2. Here there's only one thing that could have possibly happened, and that's we hit that curve, we hit it at that time, therefore the value is 2 minus 4 times that time. So far so good, and you can see that with a very simple martingale we're actually picking up the tau in a linear fashion. So if we take an expectation, we'll get exactly the term that we're looking at. So whereas this didn't quite work with the simple Brownian motion martingale in the previous problem, it looks like it's going to work here. So by optional stopping, expected value at the hitting time is the same value as it was at 0, which is 0. So let's see what we get. The right hand side here matches the left hand side, that's the 0. And on the right hand side I just have to take an expectation of w at time tau, and that's going to be 2 minus 4 expected value of the hitting time. So this turned out to be pretty easy. Move the 2 over to the left, divide by 4, and you get a half. And so with this problem we're expecting the crossing time to be roughly at the midpoint of the plot below. So if I simulate a bunch of these, you can kind of see that I'm landing, on average, if we average all these out, we should get a half, and that seems to be what's happening. So you can see that roughly these are all landing, around the value half, with a few deviations that hopefully don't occur too many times. Okay, so the next problem in ROS is 21, which is actually quite similar, but it's sort of packaged a little bit differently. So what ROS does is starts off with a Brownian motion with a volatility sigma and a drift mu. So W is still the standard Brownian motion, meaning starts at 0, unit volatility and no drift. What problem 21 does is defines the Brownian motion with volatility and the drift. Mu is the drift and sigma is the volatility, and ROS assumes both to be positive, and the stopping time that ROS defines is this one. So just looking for the very first time that x, the Brownian motion with drift, touches the value x, and x here is also, I believe, to be assumed to be positive. Well, let's see if that matters. I don't remember if that was an assumption. And ROS asks to show that the expected time at which this occurs is going to be x over mu. So I do think that x has to be strictly positive in this example, and I think I just forgot to write that down. Oh no, I didn't forget to write it down. It's right here. Okay, and you can see kind of how why it makes sense. And this is kind of what you should do with every kind of expression, is to evaluate how reasonable it is. So why can't x be negative here? Well, because we're looking at an expected value of a time, which is non-negative by definition. So this answer would make no sense if x was allowed to be a negative number. The second way to check it is, let's look at what happens when we substitute different values of mu. If mu is small, the expected value becomes large. So in other words, if the drift, which is going to give a tendency to the process to move up because mu is positive. So mu positive, a small number, would give a small tendency for the process to go higher and higher over time. And a large mu would give it a very fast and sharp tendency to move up. And so here, if mu is small, the time at which we hit x is expected to be large. That makes a lot of sense. If the process has a small tendency to go up, it's going to take a long time to reach x. Whereas if mu is very large, you have a very sharp tendency for the process to go up very, very fast, and it's going to hit x much faster. So the answer that ROS is suggesting makes a lot of sense. Let's see if we can prove it. We again need a martingale. I'm again going to skip to the most obvious basic choice, which is the Brownian motion. As usual, the next step in the program is, let's try to find out what the value of the martingale is at the time tau. Notice that the martingale choice is different here than the choice of the actual process. The process was x, the Brownian motion with drift. The choice of the martingale is actually the one that's constructing the process x, not the process itself. In fact, x is not a martingale. So now we're going to work the definition a little bit. If tau is the first time that x hits the level little x, plugging in the definition of x, we have this formula here. So now tau is written in terms of the first time of a Brownian motion, which we can rewrite like this. So in other words, the first time that x hits the level little x is the same thing as the first time that the Brownian motion hits the level x minus mu t sigma. And in fact, this is not a level, this is a function. And this should remind you right away of the previous problem. So the picture once again looks very much like in the illustration below me. So this thing, except now the slope is equal to minus mu over sigma. That's the slope of that line. And at t equals 0, we get x over sigma. So the starting point, the value 2 there, is actually going to be x over sigma. But it's, at this point looking to be the same exact problem, but just with a bunch of variables. And all of these divisions, you kind of have to be a little bit careful. Let's see. Do we need to be careful? Not so much. This is an equality, so dividing by a negative number is fine. So yeah, it looks like even if mu and sigma were negative numbers, you could still carry out that division. Okay. Now, what's the value of the Brownian motion at the hitting time? Well, you just plug in exactly what happens. So it's very similar to the last problem, except now it's in terms of variables. The value of w times tau is x minus mu tau divided by sigma. Optional stopping, what does that give? Well, one side evaluates to 0 as before, because the Brownian motion starts at 0. And the other side we have to plug in. And if we do plug it in, by linearity of expectation, we again pick up expected value of tau, which is exactly what we wanted. And this, after simplifying, gives us exactly what we want. So it's interesting that the answer doesn't depend on the value of sigma. So the volatility of the Brownian motion didn't really matter in terms of the expectation, only the drift, right? Meaning the tendency for the Brownian motion to go up. And when I say Brownian motion, I now mean x, not w. It's only that tendency that determines how quickly this event happens. So this worked out pretty well. You can try to think about where this would go wrong in the case when x was, perhaps negative, and see where kind of the logic would break down. So one place it could break down is in the conditions of the optional stopping theorem. The other idea is kind of just, let's think about it intuitively. If x is positive, if x is negative and mu is positive, then the level x is, let's say, here, and the the Brownian motion has a tendency to go up, so maybe it never actually hits the level x. And you can kind of moreover think about sort of the signs of mu and the signs of x together. If mu is negative, the process has a tendency to go down, and so you'd then hypothetically reach the level x sooner. And now the two negative signs, the one on x and the one on mu, will cancel out, giving you a reasonable answer. So it's very possible that here it's just the conditions of the optional stopping theorem are the ones that kind of collapse when you take x to be negative, because the answer it would give you is nonsensical. You can't have an expectation of a thing that's non-negative give a strictly negative result. Okay, so let's look at problem 24, which has a star on it, and the star, I guess, means maybe a higher difficulty level. So let's see how this works out. The setup looks the same. So again, x is a Brownian motion with drift. Mu and sigma both positive. And now the time tau is again the same. So is the level x. And I guess the only difference is now is that Ross is looking for the variance. So kind of like the kind of like an uncertainty interval on the hitting time. So whereas here we're saying that the expected hitting time was x over mu, the variance in this case would say sort of roughly what are the bounds within which we can expect that answer to occur. It's standard deviation, in other words. So if we take the square root of this of the right hand side there, that's going to be kind of plus or minus that value. That's the likelihood around the expected value that we have. So now let's look at the solution. This would first of all involve the definition of variance, which I've written here, and you can see how this part of the problem is done already. We're just going to plug in the previous, the answer for the previous exercise squared. And the thing that's new looks to be this term right here. So we're going to have to somehow figure out how to get at tau squared. And I already mentioned this part. So now, the martingale that we pick is going to somehow have to give us a term that involves the tau squared, which may be a little bit more tricky. And sometimes it's hard to see in advance kind of what to pick, so you just end up picking what you know. This is the martingale that we've seen before. We're going to try to pick it. Hopefully we get a tau squared somewhere there. This again is the definition of the stopping time, and we've already had practice before writing it not in terms of x but in terms of the Brownian motion. So we did this on the previous slide right here. Right? So now we're at this point, and let's see what happens when we actually evaluate the martingale at the hitting time. So we take this and expand it, and we get kind of a complicated, relatively complicated quadratic. So we have a linear term. We don't necessarily care too much about that, but once you expand the quadratic term, you get exactly what you want. This is the guy we're after, the tau squared. And from here on out, it just looks like algebra. So we're going to use optional stopping. We're going to plug in the left-hand side and the right-hand side. The right-hand side is 0, so this is easy. The left-hand side is going to give us a more complicated expression. So first of all, this sigma went away. It doesn't matter because you can just move it to the other side and get 0. So you kind of multiply both sides by sigma squared, and this is where the sigma appears. So this sigma on the expected value comes from this term, it looks like, and that term got moved to the side where 0 was. And now all that happened is that the numerator, which is this guy, got hit by the expectation, and it looks like here we have exactly what we wanted, and from here on out it's just substituting all the things that we know. We know the expected value of tau is x over mu, so that cancels the x, should cancel the mu and put an x squared. Okay, so this part looks right. So this step is obtained by substituting the expected value of tau. X squared in the front stays the same, and this is what we're after in terms of solving. And sigma times expected value of tau gives us this term, and so on and so forth. You just keep going and you get this result. So this is what the final answer is for the expected value of tau squared. And now we just go back to the variance and plug in. Well, the variance is going to be the difference of expected value of tau squared minus the expected value of tau, the expectation squared. And that's exactly this guy. So, therefore, we're done. Right, so that worked out, and to confirm, you have exactly the answer that you sought. So a bit more complicated. We ended up using a different martingale, but still it's kind of like we're juggling the same ones, either the Brownian motion or the squared martingale. I'll talk a little bit about the one from your homework now. So if you do try to verify conditions of optimal stopping for the martingales of the previous problems, as Ross sort of suggests, that's going to be tough to do. And so there are some tricks, but it gets complicated pretty quickly. So I think it can be done, but it's going to require a lot of sort of trickery. The upshot is that these problems, all of the ones that were listed, can actually be done using this, what's called exponential martingale. So you show that this is a martingale in your homework, and in fact you can use it to get a solution to this problem just as well. And the kind of attractive part of this exponential martingale is the fact that it actually satisfies conditions of optimal stopping. So let me just quickly show you how this works, and you have a similar problem on your homework. So what we're going to do is First, starting from this martingale here, and you can see how it actually is kind of flexible because it has a parameter theta. So for any parameter theta, this will be a martingale, which is what you show in the homework. What you can do is then try to rewrite it in terms of the process in the problem. The process in the problem was x, the Brownian motion with drift. So all I did here was just try to rewrite the martingale in terms of x. And you know that's easy. It's kind of the trick is to cancel out what you want to add in. So I wanted to add in the x, and now I just need to cancel it out. So this part cancels out the sigma wt term, and this part right here cancels out the drift term. The 2 is there because of the division by 2 outside, so this division by 2. And what's next? So next we need to try to argue that m, or the stop version of m, is in fact bounded. One nice thing is that the exponential martingale is always bounded below. So this is e to the something. E to the something never goes negative. So we have a kind of a lower bound for free, and all we need is an upper bound. So we're going to look for an upper bound for the stop process. So this is m evaluated at time t minimum with the actual hitting time. And now by the definition of that hitting time, you can very easily spot that this is the case. X is always going to be either somewhere below x, or once it hits x, it just stays there. This is the stopped version of the process x. Right? Once it hits the level x, it stops, and therefore it's always smaller than that, or stays below that level. And that's enough to deal with this term. So now we know that this term doesn't get kind of out of hand. It doesn't get too large. It's bounded by e to the little x. And now the question is, what do we do about these other terms? Let me clean things up a little bit. What do we do about these other terms? So this term is okay. This term is okay because it's always negative, right? There's a negative sign in front of something positive, and so this part here is bounded by 1, right? E to the negative something is always bounded by 1, so we don't have to worry about that either, provided that t and mu are both non-negative, which they are. Theta is squared, so that's non-negative. And this is the last kind of term that's a concern, perhaps, but this is where we get a little bit of leverage from this theta. Let's just set theta to be sigma, in which case the middle term goes away, gets crossed out, and what you conclude from that is that m stopped at time tau is bounded above by e to the x, and therefore conditions of optional stopping are in fact satisfied. So you have a homework problem where you get to practice a little bit with this exponential martingale, and in a similar way you can apply it to solve the previous problems from Ross. So next we're going to move on to definitions of the Brownian motion. That's the next clip.